right, we're good? Good to go? Okay. Hello, everyone. I'm Daniel, and I would like to present to you a neural dynamic model that perceptually grounds nested noun phrases. The motivation for this model is a more long-term goal to build a dynamical systems model of the neural processes that realize language understanding. That model is embedded in a larger dynamical systems model of embodied cognition developed at our institute. I'd like to start by clarifying some of our theoretical commitments, which will hopefully make it easier to understand where we're coming from. We are committed to a conceptualist semantics, according to which humans understand a word by virtue of possessing a concept denoted by the word. So, for example, they understand the word tree by virtue of a tree concept. That is some mental representation or neural representation that characterizes what a tree is. Or they understand the word below by virtue of a concept of belowness. That is some mental representation that characterizes what it means for an object to be below another object. We are also committed to a compositional semantics, according to which humans understand phrases by activating the concepts denoted by the individual words and combining those concepts in accordance with how the words are arranged syntactically in the phrase. Thirdly, we are committed to what might be called the nested nature of language, which is exemplified by the class of noun phrases with prepositional phrases, a simple example of which would be the tree below the lake. An important property of prepositional phrases like below the lake is that the object of the preposition, in this case the lake, is itself another noun phrase. So this means that we can take the entire noun phrase, the tree below the lake, and insert it as the object of a more complex noun phrase form, for example, the tree to the right of the tree below the lake, or some other arbitrary combination of nouns and relationships. Finally, we are committed to the existence of conceptual structure, a notion going back to the linguist Ray Jackendorf, which is a hypothesized cognitive representation which characterizes the meaning of a phrase as a combination of concepts. So we hypothesize that when we hear a phrase, natural language phrase, some natural language processing system converts that phrase into a representation of its conceptual structure. In the case of nested noun phrases, this conceptual structure must specify which objects there are, which concepts characterize these objects, and which relationships the objects bear to each other. So this could be visualized as a graph like this. Unfortunately, it's very much in the bottom of this beamer. I hope you can still see it. So each box here corresponds to one object and is labeled by the concepts that characterize those objects. Each arrow corresponds to a relationship and is labeled by the relational concept that characterizes that relationship. So this graph here encodes that there's a tree which is to the right of another tree, and that other tree is both below the lake and above the house. You can see that this characterizes the conceptual meaning of the phrase, the tree to the right of the tree, which is below the lake and above the house. So our goal now is to build a neural process model that can search the object referenced by a given nested noun phrase in a given visual input. So we assume that we have a neural short-term memory of a conceptual structure, and we have a process of compositional search which identifies an arrangement of objects in a given visual input, which is correctly described by this conceptual structure. So in this example here, the model has identified a tree. So this is a map viewed from the top. That's not so obvious. There's a tree which is to the right of another tree, and that other tree is both below the lake and above the house, which is the correct arrangement described by this conceptual structure. Our model is based on dynamic field theory, a framework for building biologically realistic neural process models using continuous time recurrent neural networks. The basic building blocks in DFT, dynamic field theory, are so-called neural fields. A neural field models the activation of a population of neurons as an activation function U, which is defined over arbitrary feature dimensions X and evolves in continuous time T according to a differential equation or dynamical system. This is probably best understood by an example. So here we see a neural field evolving in time that field models spatial attention to locations in a visual input, and therefore is defined over the two spatial dimensions of the visual input. We can see that the field forms so-called peaks of activation, which are a tractor state of the dynamical system and are color-coded in yellow here. So this peak, for example, models that spatial attention is currently directed to this. And a peak can be destabilized if some conditions are fulfilled, so that a new peak may emerge somewhere else. So now spatial attention is to the right. Fields can be coupled to each other, which means that the output of one field serves as input to another field. And this way, architectures can be built. So here we see our architecture, which we're going to go through step by step in the upcoming minutes. But yeah, for now, just what I want to show to you is that by coupling many fields to each other, you end up with a single dynamical system evolving in continuous time, which models the activation of many populations of neurons, which together exhibit some complex cognitive behavior. In our case, finding an arrangement of objects described by a given nested noun phrase. So the first challenge that we had to solve was to build a neural short-term memory of conceptual structure. And any such neural short-term memory must solve what's referred to as Jacobov's challenges. One of these challenges is called the problem of two and is exemplified by the phrase, the small tree above the big tree. The challenge here is that a neural representation has to encode that there are two trees, so two objects characterized by the same concept, one of them small and the other one big, which requires some possibility to bind the representation of small to a representation of tree and to bind the representation of big to another representation of another tree. A related challenge is referred to as the massiveness of the binding problem and is exemplified by the phrase, the lake above the tree above the house. The challenge is how may a neural representation encode that there's a single tree, which is part of two different relationships, the lake above the tree and the tree above the house. This is called a binding problem because it requires the possibility to flexibly bind a representation of a tree to two different relationships. In order to address Jacobov's challenges, we assume that language preprocessing embeds objects into a discrete index dimension. So, for example, the tree gets an index 1, the second tree gets an index 2, the lake index 3, and so on. This index dimension may then serve as a binding agent, which enables a neural short-term memory to encode which concepts characterize a given object. So we introduce a field defined over this object index dimension and a discrete concept dimension, and a peak encodes that the object with the respective index is characterized by the respective concept. So this activation pattern here encodes that object 1 is a tree, object 2 is also a tree, object 3 is a lake, object 4 is a house. And this is a different activation pattern in the same field, which encodes that object 1 is a small tree and object 2 is a big tree. So we can see how this solves the problem of 2, because both trees are receive a different object index, which allows us to correctly bind this small to the first tree and big to the second tree. We further assume that language preprocessing also embeds relationships into an index dimension. So the first relationship, the tree to the right of the tree gets an index of 1, the tree below the lake an index of 2, and so on. This then allows us to use that index as a binding agent as well, which then enables neural short-term memory to bind objects to relationships. So with these three fields, we are now able to encode an arbitrary relational dependency structure among objects. The first field is called the target relationship field, defined over the object index dimension and the relationship index dimension, where a peak encodes that the object with the respective index is the target object of the relationship with the respective index. So the target object is the first object, like for example, the tree to the right of the tree, this first tree is the target, or the tree below the lake, this tree is the target. And now, for example, this peak here encodes that the object with index 2 is the target of the relationship with index 2. So this encodes that this tree with index 2 is the target of this relationship below with index 2. And also the same tree is also the target of the relationship with index 3, the tree above the house, which is encoded by this other peak. So same object index, different relationship index. The reference relationship field does the completely analogous thing for the reference role, which is the second role of spatial relations. So for example, in the tree below the lake is the reference object. So this is encoded by having object index 3 being the reference of the relationship with index 2, encoded by this peak here, for example. And finally, a relationship concept field is defined over the relationship index dimension and relational concept dimensions. So these are short for left, right, above, below, or some arbitrary other relational concepts. And this peak, for example, encodes that relationship with index 1 is characterized by the relational concept to the right of. So this encodes that the relationship with index 1 here is characterized by the right of concept. So taken together, this whole activation pattern encodes all of the relationships and is able to encode arbitrary relational structures in a neural short-term memory. The next challenge that we had to solve was to couple this model of conceptual structure to a model of compositional search, which finds an arrangement of objects in the visual input that's correctly described by that conceptual structure. For this purpose, we introduce a target production field, which autonomously selects an object index to find next. When an object with the respective concepts has been found, this peak is destabilized, the location is remembered, and the field can select a new object index to find. When an object index has been selected for search, we need to look up which concepts characterize that object. For this purpose, we introduce an intermediate field which receives input from the target production field in the conceptual structure and forms peaks for all the concepts that characterize the object with the respective index. So in this case, object 1 is a tree. So there's a peak on the tree concept, which is then read out and feeds into a model of search, which identifies an object in the visual input that is characterized by the tree concept. Somehow the video is stuck. There we go. Okay, so this is now the scene, and we can see that it's now searching for a tree in that scene and selecting a candidate tree. Analogous mechanisms then also lead to look up which relationships characterize the selected target object. So in this example, object 1 is characterized as being to the right of object 2, according to the conceptual structure. So this then leads this compositional search system to search for an object which is to the right of a previously remembered object 2, or rather for a tree to the right of object 2. And object 2 has been previously remembered in a mental map and has been identified as the tree which is below the lake and above the house. So we can see then that the final object that we end up with is indeed the tree which is to the right of the other tree, which is both below the lake and above the house. So to conclude, we presented a neural dynamic process model that can search or perceptually ground arbitrary nested noun phrases. So perceptual grounding is just another way to refer to linking the language expression to the visual sensory input in our way, in a sense, to search for the objects. That model is consistent with neural principles formalized in dynamic field theory and features a short-term memory of conceptual structure, which is filled by a language preprocessing system and provides input to a neural process that generates a sequence of searches that together successfully find the described object. Thanks for your attention.